Hi, shout out to Cameron Wolf for sharing these slides on Twitter. At a high level, ChatGPT, Galactica, Lambda, Sparrow, and Palm all are large language models. Now you'll notice that this is a decoder-only architecture, and what that means is the neural network only really decodes from text to output, meaning that it only does generation. This is in contrast to other models where you have an encoder step where you take the inputs and you encode it into a certain set of neurons, and then you do the outputting separately using the decoders. So the decoder architecture is more simple, mapping directly from inputs to generated outputs. On the left-hand side, you see that it's a feed-forward neural network, and it's got this concept of masked self-attention. What that means is that it can't, the masked part means that the future tokens or the words are not visible to the neural network. And the self-attention part means that it's weighting certain words more heavily than others. So this is effectively a way to do auto-regression, meaning it's able to kind of predict future tokens in the same sequence. We also need to define a loss function, meaning like what is the error that we're trying to reduce. And here the error is, incorrect predictions of the next word given a sequence of words. So this looks like fancy math, but it's really a simple concept that we basically want to try to train the network to predict the next word. Next, we have the concept of model training. The first part of it is actually the more expensive part where we're doing the pre-training, meaning we're crawling over a huge corpus of data, usually the entire internet or something close to it. And you're basically looking at sequences of words like the chicken crossed the road or the student aced the test. And you're trying to predict the next word and refine the model over time. And then you take it and apply this to the downstream task adaptation, which includes two main options, either doing fine-tuning or using zero or few shot prediction. For fine-tuning, you just give the model a bunch of essentially human selected examples of how you want the model to predict things. And you basically run gradient descent on these handful of examples to essentially bias the model towards a certain style of output. There's an interesting observation that the larger models actually require fewer samples of training data to essentially reach the same performance. So a lot of companies have been just adding more and more parameters to their models to make them bigger and essentially better without really doing any additional engineering work. But it also shows in the data that you really want to have sufficient data to train a really large model. A lot of times these smaller models like Chinchilla will outperform the larger models if they just train for more cycles and against a larger data set. So it's a balancing act in terms of model size and data set size for training. To improve performance further after the initial training, you can do supervised fine-tuning. This just means that you collect a set of data where you have example inputs and example outputs, and you just run gradient descent on this set of data. And it kind of fine-tunes the model to kind of generally output in the style that you want it to. What's interesting about reinforcement learning human feedback is that you train an entirely separate reward model where you ask the model an input question and you sample 4 different outputs from the model, and then you ask a human to rank the outputs from best to worst, and then this set of rankings is used to train this separate reward model. Then you take the separate reward model and you apply it to train the original model, and that basically creates a scaled up way for the human insight to drive further training for the large language model.